So I'm here again on a very hot summer day at the Technical University of Graz. I think, is that how you pronounce it?
Graz, yes.
Graz, Austria, at the European Astrobiology Network Association's 2024 conference meeting here. And one of the people from a local institution, the Institute for Space Studies, is it?
Space Research.
Institute for Space Research. And also you are a member of the Austrian Academy of Sciences?
Yes, that's the Institute of the Austrian Academy of Sciences.
The Institute of the Austrian Academy of Sciences is with me. I've been speaking to him. And he was also the co-eye of the NASA's InSight mission, which was by anyone's notion, was a grand success. Although the instrument, Guenter Kargl, that you worked on, you were the co-investigator on, did not, due to unforeseen circumstances, did not turn out as expected. Can you explain?
Yes, it turned out the soil behavior at the landing site was completely different to any other soil we have seen before with all the rovers and landers we had beforehand. And therefore, when we tried to insert our penetrator to dig down to 5 meters depth, the soil crumbled around this device and couldn't provide any side friction anymore. And this was most likely one of the reasons we couldn't penetrate actually deep down as we would like to.
And your device was essentially a pile driver.
It was a pile driver with so a nail with an inbuilt hammer, so to speak.
Right.
And it's recoil compensated inside with some spring system and countermasses, but you still need a minimum amount of side friction on the walls to press against the side walls of the borehole you're creating.
And essentially, even though you had done simulations, computer simulations, on what this would look like actually when you were on Mars, your simulations did not match the reality that you faced once you landed.
Well, actually we did also lots of lab testing with the real hardware, including measurements in the desert, in the Mojave, for example. And all the time it worked nice. And we tried to match up the soil simulant we were using to match it up to regolith, as we knew it from all the rover missions. On site, on Mars, it didn't work because apparently the properties of the soil at this landing site, which was a filled-in impact crater, did behave completely different, and therefore it didn't work as predicted.
And where was the landing site again?
This was roughly 300 kilometers north of the Opportunity rover.
Opportunity rover. And what is the region? What was the name of the region?
Sorry, I forgot the name of the region. You need to look it up.
That's okay.
Yeah.
All right. Anyway, but basically we missed out by your instrument not being able to take its science data. We missed out on obtaining the heat flow from the interior of Mars, and tell us why that's important.
To measure the heat flow of a planet tells us how fast the planet is losing energy. From the formation process, we know that the interior of planets are really hot. Even today, they are really hot. Sometimes they are even hotter than the surface of the sun. And if you want to know about plate tectonic, magnetism, how to create that, and how volcanism works, you need to know how much energy is in there and how fast the planet is losing this energy. And the only way to measure that is planetary heat flow.
And so essentially, it doesn't look like we're going to have another geophysics mission to Mars, a dedicated geophysics mission to Mars anytime soon, does it?
Unfortunately, it doesn't look that way, and I would say we are missing out on our homework. Because if you really want to understand planets, we need to understand the interior and how the interior works.
So you think, in your own opinion as a geophysicist, a planetary geophysicist, that Mars, even the moon, has been neglected in terms of exploration by not putting more emphasis on geophysics and geodynamics, even though geodynamics is not your field?
Yeah, there's always a big competition for money and mission opportunities, and at the moment everyone is concentrating on finding life or traces life or conditions for life.
Those are the sexy topics.
And it is more sexy, and therefore the just plain old boring understanding how it works got the second seat. And that's why we are missing out on missions to understand this kind of interior behavior of planets completely. And keep in mind that InSight delivered this huge surprise that apparently the Mars core is liquid all the way down, which nobody expected.
Right. So how does understanding the interior of Earth, the interior of the Moon, the interior of Mars, and hopefully in the future the interior of Venus, how will that help us interpret exoplanetary systems that we are only being able to, we can only see remotely? We are not able to send probes to the surface of these exoplanets.
Yeah, if you want to understand the formation process of a planet, how it evolves and how it will evolve in the future, because planets are not static, you need to learn how they tick into the interior. And so far we have only one planet where we have fairly decent understanding, that's Earth. But even here we know that sometimes our models are maybe not exactly predicting what we are seeing. Just keep in mind earthquakes, plate tectonics, volcanism, or the general behavior of a rotation pattern, this kind of stuff. This is all playing a role, and this is the planet keeping us alive, keep in mind. And if you want to understand exoplanets or any other planet, we need to have a complete understanding of all the physics going on, and all physics and chemistry, I would say, actually, going on inside the planet up to the surface of the planet. And the surface is not isolated from the interior. There's a lot of interaction, even on a planet which seems to be as dead as Mars.
So thank you so much, Guenter. Fascinating hearing your insight about the InSight mission. Thank you so much.